How much a material stretches for a particular amount of applied force depends on the dimensions of the material. So, for example, if you use a thin wire compared to a wider wire, how much it would stretch depends on the width of the wire. And if we want to compare it to another material, so for example, when we want to compare between copper wire to aluminium wire, we need to use something called the stress and the strain of that material. So, if a tensile or a stretching force is applied on a material, we can calculate the stress experienced by that material by dividing the force by the cross sectional area of that material. What we mean by the cross sectional area is if we imagine the wire to be a cylinder and we were looking directly down one end of the cylinder, we would see a circular face. So, this is the cross sectional area of this wire. So we can calculate the stress on this wire by dividing the force we are applying on the wire by the cross-sectional area. And we know we measure force in newtons and area is measured in meters squared. So the unit of stress becomes newtons per meter squared, which is equivalent of pascals as well. So from GCSE, you should know that pressure is also measured in pascals. So it does have the same unit as stress. Often in A levels, you will see that units are asked to be expressed in terms of their base units. So let's try to see that if we can convert the newtons per meter squared in terms of its base units. So always, whenever we are doing expressing it in terms of base units, it's useful to start off with an equation. So we can express newtons per meter squared as force over the area. So we know force is equal to mass times acceleration, and area of a circle is pi r squared. And we know we measure mass in kilograms and acceleration in meters per second squared. And we also know that area is measured in meters squared. So if you want to cancel out the square from the bottom with the meter from the top, we are left with newtons per meter squared, becoming kilograms per meter per second squared. So this is now expressed in terms of the base units. Another useful quantity we have to know when a tensile force is applied on a material is the strain the material goes through. So we can calculate the strain using the change in length divided by the original length the material had, which we are going to express in terms of symbols as x over L. And because both of these are length measurements, so this turns out that the strain does not have any units because both of them are measured in meters, so they would cancel out and we would end up with no units for strain. So strain is usually expressed as just a number, and it can also be expressed as a percentage. And if you are applying a tensile force, the value of that strain is going to have a positive value. But if it's a compressive force, the strain ends up having a negative value. So, the main thing to remember about stress and strain is that stress causes strain, which means that when you're applying a force over a particular area, it will cause the material to go through a change in length. So, next we're going to look at stress against strain graphs. And there are a few important things you have to know about these types of graphs. So, let's go through each one one by one. The first point is represented using the letter P, and this represents the limit of proportionality. And just like you had in force against extension graphs, up to this point, Hooke's law is being obeyed, which means that the stress and the strain are increasing at a constant rate, and that gives you a straight line up to this point. Slightly above the proportionality limit, you've got the elastic limit, and this is up to the point where the object still returns back to its original shape when the force is removed. Next, we have the yield point, and this is the point where the material starts to deform permanently. So, once we exceed this point, even after we remove the force, the material won't go back to its original shape. So, now it has gone through plastic deformation, and this is where it is changing permanently. So, up to the elastic limit, the material can still recover, but beyond the yield point, the material will not recover and it will be deform permanently. The next very important point we have to know from the graph is the UTS, and this is crucial because it tells us the maximum stress a material can withstand before it will break. So it is especially important in engineering or construction and manufacturing for several different reasons, like what type of material to choose, or whether it's safe to use or reliable to use. So the UTS, which stands for the ultimate tensile strength, is very important property that we have to know about for materials. The next point is called the breaking point. And when we are increasing the stress on a material, like for example, if we are pulling on a rubber band, and as we stretch the rubber band, the atom starts to get pulled apart. So eventually the atoms are going to separate completely. This is when the rubber band is going to snap and break. So on the stress and strain graph, this is where the graph stops at the end point, and this is indicated by the breaking point. We can also calculate the area under the graph, indicated by this shaded region here, just like we were able to do so for the force and extension graph. And this is going to give us the elastic strain energy, or the energy that is stored per unit volume of the material. So that becomes E equals half times the strain times the stress of the material. The last thing we need to know about this kind of a graph is the gradient of the graph, which is simply stress over strain. And this turns out to be a constant up to the point of limit of proportionality, because the graph is a straight line up to that point. But beyond that, when the graph starts to curve, the Young's modulus is no longer constant and it starts to change. What type of uses a material might have depends on how it behaves under stress and strain. So, for example, a brittle material suddenly breaks without any plastic deformation. So, for example, if you have a chocolate bar and you snap the chocolate bar, it will immediately break without going through any plastic deformation. Whereas a ductile material will go through large plastic deformation before it will break. For example, copper is a ductile material, which is why it's very useful to use for making wires, because we can stretch it out and turn it into electrical wires before it breaks. The Young modulus is a measure of the stiffness of a material, and it is used by engineers to make sure the materials they are using can withstand sufficient forces. And it is actually independent of the dimensions of the material, which means whether the material is wide or thin or very long or short, it's not going to affect the Young modulus. The Young modulus has a symbol E, and as we know that energy also has the same symbol E, so we need to look at how are we calculating the quantity to be able to differentiate it. So to calculate the Young modulus, we are going to divide stress by strain, and this will have the same unit as stress, which is pascals or Newton per meter squared, because we know that strain does not have any unit. And like we said before, when we plot the graph of stress against strain, the gradient of the graph equals the Young modulus.